Hi, welcome to this video of AQA P1 physics. We're going to be, in this revision session, we're going to be looking at heat transfers, energy and efficiency, and generating electricity. So the first half of the specification for the P1 unit. Okay, so the unit starts off by looking at infrared radiation, and what you should know about infrared radiation first and foremost is that it is an electromagnetic wave. Part of the electromagnetic spectrum, one of those 7 types of radiation that all travel at the speed of light. You also need to know that all objects emit and absorb some infrared radiation, and the amount that they emit and absorb depends on how hot they are. The hotter the object is, the more infrared radiation it will emit. So you will remember that we look at 2 different types of surface when we're looking at infrared radiation. We have the dark matte surfaces, and we have the shiny light surfaces. So the dark matte surfaces are good at absorbing infrared radiation. They are good emitters, which means giving it out. And they are poor reflectors. The shiny light surfaces are poor absorbers. They are poor emitters, and they are good at reflecting it. So when you're answering an exam question that's looking at things with a light shiny surface or a dark matte surface, what you want to be paying attention to is where the heat transfer is coming from. Which object has more heat? If you are looking at the heat coming from within the object, for example, if we have an oven, then we want to know whether it's going to be a good emitter or reflector. So we want, ideally you'd want the heat to be reflected on the interior to keep the heat in, and it to be a poor emitter on the outside. If we had an object, for example, a solar panel, the heat source is on the outside, that's the sun, we'd be interested in whether it's a good absorber. So our solar panels are painted black because that's a good absorber of infrared radiation, and not a light shiny material because that would reflect the infrared radiation and therefore wouldn't heat up the water. That brings us on to kinetic theory. Kinetic theory is just the theory of how particles work in solids, liquids and gases. So, things you need to remember. In a solid, there is a regular arrangement of particles, and the particles are close together. There are really strong intermolecular bonds as well. A liquid, by contrast, it has an irregular pattern of molecules. The molecules are still close together though, they're still touching. And the bonds are fairly strong, although particles can slide past each other, they can flow past each other. So the particles flow in a liquid, whereas in a solid the particles vibrate around a fixed position. In a gas, the particles are randomly arranged. They are far apart, and there are weak or no bonds between them. And the particles can move freely. Okay, so that's what you need to know about what's going on in the particles. As an object's heated, the particles are going to gain more kinetic energy, so they're going to start to move around more or vibrate more if we're talking about a solid. And when a change of state happens, the energy that's going into the material is used to break bonds. Okay, so that leads us on nicely to the energy transfers by heating, and we've got two transfers here. The first one is conduction. In conduction, we are looking at solids, in particular metals, because these have what we call delocalized or free electrons. And because these electrons are free to move through the particle, that means the energy can be transferred a bit more quickly than it would be otherwise. So what we've got going on in this image, near to the heat source, these particles are going to start to vibrate more. They were already vibrating, so we say they vibrate more. As they vibrate more, they collide with the adjacent particles. That collision enables them to transfer their energy. And that energy transfer is obviously then where the energy gets passed along as heat. Our second form of energy transfer here is convection. In convection, we're looking at fluids. So fluids are liquids and gases. Basically, we need the particles to be able to move around freely, which can't happen in the solids. We heat up the fluid nearest the heat source at the bottom of the container usually, and that causes the particles to move apart. When the particles move apart, that means the warmer fluid is taking up more volume but still has the same mass, so the density becomes less. Where it's less dense, that enables it to rise, and the cooler fluid from the top falls down to take its place. And that sets up what we call a convection current, so an ongoing process. Convection currents are found quite commonly. In chemistry, you will have looked at them in terms of plate tectonics and what enables the different plates on the surface of the Earth to move around. That's because of the convection currents in the mantle causing the plates to move either apart or towards each other. And you should also know that the wind is caused by convection currents in the atmosphere. So as the heat from the sun heats up part of the atmosphere, that part of the atmosphere rises and cool air comes in to take its place, and that movement of air is what we feel as the wind. Heat transfer by evaporation and condensation. You need to know how evaporation and condensation can be used to transfer heat. Starting with evaporation, the first thing you need to know is that not all particles in a liquid have the same kinetic energy. Their kinetic energies will form a distribution something like this. So if we've got the kinetic energy along the bottom and the number of particles up the side, if you've got a certain fluid, the average kinetic energy is going to be what determines the temperature of the fluid. Now, not all of these particles are going to have enough kinetic energy to leave the surface of the liquid, but some of them are. So let's say it's these ones here. These particles all have enough kinetic energy to leave the liquid. So what happens, once these have all left, the result of that, the rest of them maintain the same kinetic energy as previously, but because we lost these few at the top end, the average kinetic energy has decreased. That means the overall temperature of the liquid has also decreased. So the rate of evaporation is going to tell us how quickly the overall temperature decreases. So in evaporation, it's taking energy from the liquid as those particles evaporate. Now, one of the reasons we sweat when we're doing exercise is because we want to lose energy from the body to help cool down the body. So where the particles of sweat are evaporating from the body, the energy they're taking is the surplus energy from the body. Now, condensation is a way of transferring energy out of the gas as it turns into a liquid state. And what's happening there, for example, let's say that I put my hand into the steam from the kettle. As the steam hits the cooler surface of my hand, it condenses onto my hand. The heat energy that was in the steam goes into my hand, and that's what causes burns on my hand, because it's got that extra heat energy that wasn't there before. Okay, the factors that affect the rate of heat transfer that you need to know. The first one is surface area to volume ratio. The larger the surface area, the quicker heat can transfer in and out of the object. The material from which the object's made. So if the material is a good conductor, if it's made of metal, heat transfer is going to be quicker than if it's a good insulator. An insulator just being a material that isn't very good at conducting heat. The nature of the surface with which the object is in contact. So again, we're looking at the material. We're also looking at the colour like we did with the type of radiation. And then temperature difference. Note that keyword difference. It's really important that you don't talk about just the temperature. It's the temperature difference between the two objects between which heat is being transferred. The bigger that difference is, the quicker the heat's going to transfer. Okay, so we can then apply that to heating and insulating buildings. So the first thing we need to look at in this is U values. U value tells you how good an insulator it is. Okay, you need to know that the lower the U value, the better the insulator. Okay, you also need to know about specific heat capacity. The specific heat capacity of a material tells you how much energy it can store in 1 kilogram of material if we've increased the temperature by 1 degree. You get given the equation for specific heat capacity on your equation sheet, which is E equals mc theta. Okay, E stands for energy, M for mass, C is the specific heat capacity, and theta is the temperature. The unit of specific heat capacity, which they quite often ask you for, is joules per kilogram degrees C. Okay, you only put in the 1 per, everything after it shows that it's underneath in the equation. So if you've been working out specific heat capacity, that equation rearranges to C equals E divided by m theta. And of course, the higher the specific heat capacity, the more energy can be stored. Solar heating, you need to know that the sun's energy can be used to heat up water, and then that water can be used to heat buildings or provide hot water for a house, say. You should know that solar panels are painted black or have a black outer coating so that they absorb more heat energy. That water is used inside them because water has a high specific heat capacity, so it can store a lot of energy. Okay, moving on. That's the end of heat transfers. We now need to look at energy transfers and efficiency. So the first thing we need to go through is the 9 types of energy. So let's see if I can remember them all. We've got kinetic. We've got thermal, light and sound, then we get on to the stores. We've got chemical, elastic potential, gravitational potential. Then the ones that people forget, electrical and nuclear. Things that people often forget, the energy that's stored in any kind of fuel or in a battery is chemical energy. Nuclear very rarely comes up. That's only comes up in the context of a nuclear power station where it's nuclear fission that is releasing the energy. Kinetic is movement, thermal is heat, and the rest you should all know. Okay, energy can be transferred usefully, it can be stored, and it can be dissipated but it can't be created or destroyed. That's what's called the principle of conservation of energy, and it's one of the most important rules in all of physics. So what that tells us is that the total amount of energy that's going into a system has to be equal to the total amount of energy that comes out of the system. And we can often use circuit diagrams to represent that. So, for example, it's very badly drawn. So this might show you the energy transfers from a light bulb. So we have electrical going in, and we have light coming out as the useful energy, and we have heat or thermal coming out as the waste energy. Now what's going to happen to that waste energy is that's going to go to the surroundings, and as a result those surroundings are going to get warmer. Now the last thing that we need to use on this one is working out the efficiency. Efficiency given to you on your data sheet, but it is the useful output divided by the total input. Okay, so that can either be given just as a decimal as it is, or you can times it by 100% to give you a percentage. Either of those is acceptable. These can be the useful output energy and input energy, or the useful output power and total input power. As long as you're consistent, as long as it's either energy both times or power both times, it will work. So transferring electrical energy, there's a big focus on electrical energy. So there are two things that the amount of energy an appliance uses depends on, which are the power rating of that appliance and the time it's switched on for. The power is either given in watts or kilowatts, and there are 1,000 watts in 1 kilowatt. Time is usually given in seconds or hours, and it's sometimes useful to remember that there are 3,600 seconds in 1 hour. To work out the total amount of energy, we use the equation energy equals power times time. And we can work out the energy in two different ways. We can work it out in terms of joules, in which case we would use watts times seconds, or we can work it out in terms of kilowatt hours, which would be in kilowatts times hours. Okay, it's really important that you make sure you're using the right units and converting the numbers that you've been given into the right units if they're not already in them. Okay, once you've got the amount of energy you've used in kilowatt hours, you can then use that to work out the cost of the electricity supply, because an electricity bill will tell you the cost per kilowatt hour or the cost per unit. Unit and kilowatt hour are interchangeable. So if it costs 14p per kilowatt hour, you work out the number of kilowatt hours used, times it by 14, and then you might need to convert it into pounds as well. Right, last section is generating electricity. So we're going to start by looking at how we can get electricity from non-renewable energy sources. So that's going to be our fossil fuels and nuclear power. So let's start off in section 1. That's a boiler. A fossil fuel is burnt or nuclear fuel fissions either of those methods create heat. The heat is then used to heat water to turn it to steam. Okay, the second section on here is what we call a turbine. So the steam turns a turbine. And that turbine is connected by an axle to a generator. So the turbine turning turns the generator. And the generator generates the electricity. Okay, we're not going to look at what happens beyond that just yet. So let's move on to look at renewable energy resources. So, renewable energy resources you need to know are wind, wave, tidal, hydroelectric, geothermal, solar, and biofuels. Okay, so wind, wave, tidal, and hydroelectric all turn the turbine directly. Now, with wind, that's the energy from the wind, which we said earlier was caused by convection currents due to the sun's heating of the atmosphere. Wave is caused by the wind blowing over the surface of water, and so the waves going up and down can turn the turbine instead of the wind doing it directly. Tidal is caused by the tides, which are the effect of the moon's gravity on our oceans. So as the moon goes around the earth and as the earth spins under the moon, that causes little bulges in the water level of the sea. And as that comes in and out through the openings of rivers or estuaries, that can turn a turbine. Hydroelectric is caused by water flowing downhill. So where you've got a stream or a river that's flowing downhill, a dam can be built across that and the water can be funneled through a turbine. Geothermal energy is using the heat from hot rocks. The rocks are hot because they are radioactive. Now, as we've looked at previously, where we've got heat, we can use it to heat water. The water turns into steam. The steam turns a turbine. The turbine turns a generator. The generator generates electricity. With solar power, we can either use the solar water heaters that we discussed earlier, or we can just generate electricity directly. So what happens in that is the sunlight hits the solar panel. That causes an electrical reaction in the solar panel which creates electricity. You don't need to know any details about that. And biofuels are any biological material that can be burnt in the place of fossil fuels in a power station. So you're looking at things like wood, you're looking at bio-oil, so things like ethanol, and you are looking at animal waste products, for example, chicken poo. Now, these renewable energy resources can be particularly useful in remote areas where they can't be connected up to the national grid, particularly things like hydroelectric being used in mountainous areas, wave power being used on islands, but even things like solar panels being used for small-scale production to light road signs. You need to be aware of some of those different uses because any of them could come up in the exam. So environmental impacts. The first section of environmental impacts you need to know about is the release of substances into the atmosphere. So the one that you'll be most familiar with is carbon dioxide. Now, carbon dioxide causes greenhouse effect, which is where the infrared radiation from the sun gets trapped in our atmosphere and doesn't reflect out of our atmosphere as much as it normally would. That causes global warming. So the average temperature of the Earth increases. As a result, sea levels rise because glaciers, for example, at the Antarctic, they start to melt. It also causes more extreme weather patterns, more flooding. generally not very pleasant. But good news, we can capture the carbon dioxide that is given out from our power plant using a method known as carbon capture. Carbon capture and carbon storage. So what we tend to do, we capture the carbon dioxide as it's coming out of the power plant. We store it in water. We take that water and we pump it into the old oil fields and gas fields. So we've taken the gas and oil to burn them. We then fill that space up with the carbon dioxide filled water, and that traps the carbon dioxide in there. Another gas that's given off is sulfur dioxide and nitrogen dioxide. Both of those can cause acid rain. So when they go up into the atmosphere, they dissolve into the water in clouds. That makes that water acidic, and then the rain that comes down is obviously a weak acid, which can cause damage to trees, to buildings, and damage animals as well. Again, we've got a solution, particularly for sulfur dioxide. We have something called flue gas desulfurization. That basically does what you'd expect. The flue is just the chimney. So as the gas goes up the chimney, the sulfur's taken out of it. That's all that means. Okay, production of waste materials. So we've already talked about carbon dioxide and sulfur dioxide and nitrogen oxides, which come from fossil fuels. If we use nuclear fuels, the waste that's produced is radioactive. So those radioactive wastes are going to be giving off radiation for quite a considerable amount of time, so they need to be disposed of in such a way that they're not going to cause harm to any of the wildlife. Other environmental impacts you need to know about are noise and visual pollution, which we particularly talk about when we're looking at wind turbines, and also the destruction of habitats, which we tend to talk about in reference to hydroelectric power. Okay, very last bit then, the national grid. The national grid is a network of cables and transformers. That's the definition you need to know. There are two types of transformer, which are the step up and step down transformer. So we've got our power station. When the electricity comes out of the power station, the first place it goes to is a step up transformer. The step up transformer increases the voltage. The reason it does that is because by increasing the voltage, it decreases the current. Yes, current is given the letter I. It's daft. Okay, so increases the voltage, decreases the current. Why is that a good thing? Well, that's because the higher the current is, the more heat is lost in the cables. Obviously, heat loss is not a good thing because that means it's less efficient. So we want to reduce that by decreasing the current. We do that by increasing the voltage. So once the electricity has gone to the step-up transformer, it then goes across the country on that system of pylons and cables. And then when it gets to near where it needs to be, we pass it through another transformer, which is a step-down transformer. Step-down transformer does exactly the opposite. It decreases the voltage. It increases the current. And the reason it does that is to make the electricity safe to go into your home. And the very last thing you need to know is that the domestic electricity supply in the UK is 230 volts. Okay, that's it for this revision session, this revision video. I hope it was helpful to you, and I will be putting more up shortly.